So to start off with this lecture, we're going to go over some practice examples of what was covered in the previous lecture dealing with the types of solids. I recommend if you haven't watched that lecture to make sure you watch it. And it goes in depth explaining the different types of solids we can have. So here's a typical question. We have a list of solids. We want to know which of the following solids is an atomic solid. And an atomic solid, if you notice, if you remember the definition, an atomic solid is a group 18 element. So atomic solid is a solid in group 18. So again, when we say solid, it doesn't mean that at room temperature it's a solid. It means at some temperature it can be a solid. So you may say, well, noble gases are gases, yes, at room temperature, but there is a temperature at which it can become a solid, and those are called atomic solids. Since there's such weak attractive forces holding those atoms together, that's why they're gases, at room temperature, and they're only solids at very low temperatures. So here we're looking for in this series which choices are from group 18. Choices are from group 18. So we'll go through each one and explain what each one is and see which one of these falls into the category of group 18 elements. So first we have P4. So you'll notice here P4 and also H2. There are only nonmetals in the formula. So whenever you're looking at a solid and there's only nonmetals in the formula, this indicates that these are molecular solids, because molecular solids only have nonmetals in the formula. So these are referred to as molecular solids. And it has to be more than one nonmetal. You can't just, for example, have P. It would have to be like P4, H2, CO2. So you have different, you have at least two or more nonmetals in the formula. That's a molecular solid. Next we get to krypton. So here you got to ask, krypton is only one in the formula, so it can't be a molecular solid. The second question is, krypton is found where on the periodic table? It's found in group 18. So this would be an atomic solid. Because again, it's a group 18 element. Next we have manganese, and it's manganese by itself. So manganese on the periodic table is a metal. So this would be a metallic solid. Next we have carbon diamond, and carbon diamond is it's one of the ones that's a network covalent solid. So it's a big entity that's connected through covalent bonds. So it's a network covalent solid. And then lastly, we have CaCl2. And you notice here we have a metal and a non-metal. So this is the characteristic of an ionic solid. So anytime you have a metal and a non-metal together, it's going to be an ionic solid. It's a solid because it has cations and anions. So that's what you ask yourself when you go through these and try to determine what type of solid it is. All right, so we'll continue. We'll look at one more example of this before we move on. So here we have a question, and let's make sure we're on mute. So which of the following solids is an ionic solid? Select all that apply. So here again, we're going to go through, and I'll give you a few minutes, a minute or two, just to look at these and see if you can identify which ones are ionic solids, and then I'll go through it and then we'll discuss it. And let's not put stuff on the chat. Okay, so now I'm going to go through it and explain what each one is, and then we'll take some questions. So again, we're looking for ionic solids. So ionic solids are held together by ionic forces. So what we're looking for are cations and anions. This is what makes up an ionic solid, and usually these involve metals and nonmetals. So in the first one, you see we have CO2, which is more than one nonmetal, and we have S8, which is more than one nonmetal. So again, these two would be molecular solids. And just for ease, I'm just going to put M for molecular solids. Next, we have helium, and helium is just one atom, and it's a nonmetal. And if we know helium comes from group 18, so this would be an atomic solid. Next, we have copper 2 fluoride. So here we have copper and fluoride, which is a metal and a nonmetal, which meets the requirements of cation and anion. So this is an ionic solid. Now SiO2, this is one of the ones that was referred to as covalent network. And then lastly, we have ammonium chloride. Now ammonium chloride contains ammonium and chloride. This is a cation and an anion. So this is also an ionic solid. So now moving on, we're going to discuss what occurs with the different phase boundaries of the phases. And the first one we're going to look at is the liquid vapor phase. So at the liquid vapor phase, we have this equilibrium or this balance between molecules of gas and molecules of liquid. And so what happens is if you put a liquid in a closed container, over time, some of the molecules of liquid will get enough energy to escape the surface of the liquid and become vapor. And then they'll fill the container that they're in. So over time, more molecules vaporize, and eventually you fill up the flask with vapor and liquid, and you've reached equilibrium. So the equilibrium means that the amount of molecules becoming vapor and the amount of molecules in the vapor phase that are condensing are at the same rate. And so this vapor that builds up in the flask is referred to as vapor pressure. And again, the vapor pressure increases until it's at equilibrium. So different compounds and substances with different types of attractive forces have different types of vapor pressure. To give you an example, if you go on a hot day, you put a gallon of water in a sealed container. Say you take a jug, fill it half with water in a sealed container, and in another jug you put some gasoline in a sealed container, leave them out in the hot sun all day. You come at the After a few hours, you open up the water one, you may not hear much of anything. But when you open up the one with gasoline, it's going to go psh, and you'll notice that the jug has been like pushed out because of the pressure that builds up from the vapor pressure of gasoline. And so what's happening is since the compounds in gasoline have very weak attractive forces, it doesn't take much energy for the molecules in the liquid phase to become vapor. And it has a higher vapor pressure than the corresponding water, because water is held together by stronger attractive forces, which means it takes a lot more energy to make them leave the surface of the liquid. Likewise, if you go on if you take your car to fill it up with gas and it's close to empty, when you go and open your gas cap, you'll hear it go psh. And what that means is that you're releasing the vapor pressure that was built up by the molecules in the gasoline that escaped and filled your container. And that's important because the pressurized gas tank is needed for cars nowadays to function correctly. And so that's what we're talking about, the liquid gas equilibrium. So this is a little bit different when we're talking about soda cans and champagne. So with soda, it's a mixture, it's a solution of carbon dioxide and water. And we'll talk more about this in the next chapter, but just to give you a little bit of a prelude. So what's happening is you pressurize the container, you push the gas into the solution. When you pop the top, you're releasing all that pressure. So as you decrease pressure, the solubility of the gas decreases. And that's why the gas comes, that's why your drink or your Coke or Pepsi gets flat over time, because the gas molecules leave the water. So that's a little bit different phenomenon based on dissolving a gas in solution. So what causes a molecule in the liquid state to get enough energy to leave the surface? This is due to a number of reasons. The heat from the ambient environment is what causes it. So if you add heat, or just at room temperature, even at room temperature, if you put something out in a bottle, it's going to build up vapor pressure. So at all temperatures, you'll have some vapor pressure associated with it. And as we'll look at in just a little bit, as you increase the temperature, you're going to increase the vapor pressure because you're adding more energy to the liquid. So now more molecules have more energy to leave the surface. But at all temperatures, there's some energy there that causes some of the molecules to leave. And it's just the heat in the surroundings. So your liquid is the system. And so this is just showing you that at different temperatures, we increase the vapor pressure because now more molecules are able to leave the surface of the water or vaporize. So the the blue curve is at one temperature, and you see there's a few molecules that have vaporized. And then we have the second temperature, which is the orange, which is greater than T1. And you see that the curve for T2,
right
here, this is
I had a lecture.
If you could put it on mute, please. I don't need to hear the commentary. So at T2, you see there's more molecules that have the sufficient kinetic energy to be removed from the surface. And so that's why when you increase the temperature, you're going to increase the molecule's kinetic energy. When it's moving fast enough, it breaks free of the surface of the liquid and it becomes vaporized. So temperature is a way to increase or decrease the vapor pressure of your substance. And again, that's why in the summertime, you may hear that it's better to fill your gas tank up at night than in the heat of the day, because what happens is During the heat of the day, the gasoline in the tanks underground uh, build up heat, and you're actually, when you fill up your gas tank, you're not getting all the good stuff that has the low boiling points. So it kind of vaporizes it. So sometimes you get some of the heavier stuff from it. So that's why it's always better to fill up your tank when it's cooler versus when it's hot outside. So besides temperature increasing vapor pressure, also the weaker the attractive or intermolecular forces are, the more easily the molecules or particles can enter the vapor phase. So for example, noble gases would have a very high vapor pressure at room temperature because they have very weak attractive forces. But something like water at room temperature would have a very low vapor pressure. And vapor pressure is inversely proportional to the boiling point. So if you have a high vapor pressure, we'll call it VP, you're going to have a very low boiling point. So if you have a high vapor pressure, low boiling point, and vice versa, if you have a low vapor pressure, you're going to have a high boiling point. And so based on the vapor pressure of a substance at, say, room temperature, you can determine, or not room temperature, but you can determine based on the vapor pressure at 1 atmosphere, you can determine the strength of that substance based on its boiling point. So things that have very high boiling points have strong attractive forces. Substances that have very low boiling points have weak attractive forces. Like, for example, whenever you open up a bottle of nail polish remover, you get that whiff of odor. That's because the substance that makes up the nail polish remover has very weak attractive forces, and it builds up vapor pressure in your bottle. So when you open the bottle, the vapor releases, and that's where you get the smell of the nail polish remover. So again, two things affect vapor pressure: temperature and attractive forces, which we refer to as intermolecular forces. The weaker the attractive forces, the higher the vapor pressure, the higher the temperature, the higher the vapor pressure as well, because now molecules have more kinetic energy. And this is just showing you a chart of how vapor pressure and temperature and so as we can see, as we change the type of attractive forces, and we can monitor how the vapor pressure changes at different pressures or different temperatures. So here we have three different substances: diethyl ether, ethanol, and water. And as we go left to right, the difference in the substances is that they have stronger attractive forces. And so you notice that at different temperatures, each substance has a different vapor pressure. But as we increase temperature, we see an increase in vapor pressure. And so at 20 degrees Celsius, which is synonymous with room temperature, you see diethyl ether has a very high vapor pressure, but ethanol and water have very low vapor pressures. And that's because diethyl ether, the attractive forces are very weak compared to ethanol and water, where the attractive forces are very strong. And so if you were to spill diethyl ether on the floor at 20 degrees Celsius, it would instantaneously vaporize into vapor. Now, if we increase the temperature, you see that now the vapor pressure of ethanol and water do increase. And the reason that 760 is identified here as a special pressure is because 760 refers to 1 atmosphere. And so when you have a boiling point at 1 atmosphere, this is referred to as the normal boiling point, which is what we use for cooking and whatnot. So for water at 1 atmosphere, water boils at 100 degrees Celsius, ethanol at 78.5, and diethyl ether at 34.5. So again, the lower the boiling point, the weaker the attractive forces are. So now how can we calculate the vapor pressure of a substance at different temperatures? And that brings us to the Clausius-Clapeyron equation. And so the Clausius-Clapeyron equation, there are two ways you can use this equation. So one is, if you know the vapor pressure at a particular temperature, you can plot the ln of P versus 1 over T. So on your, if you graph ln of P, the vapor pressure versus 1 over T, and T has to be in Kelvin, by the way. P can be in whatever unit because ln of P, the unit doesn't matter. You can do atmospheres, millimeters of mercury, etc. But temperature has to be in Kelvin. And so what happens is when you plot this, you get a linear line, and the slope is equal to negative delta H over R. And R is a constant. It is 8.314 joule per a mole Kelvin. And this is how you can determine the heat of vaporization of a substance, is by plotting this change in vapor pressure throughout the different temperatures. You get the slope. You can solve for delta H, the heat of vaporization. That's one way you can do it graphically, like this. Now the second thing, let's say we have a vapor pressure and a temperature, and we want to increase or decrease the temperature and calculate the new vapor pressure. Well, then we would use the two-point form of the Clausius-Clapeyron equation, and we would need to have the delta H of vaporization. And then we can calculate what the new vapor pressure would be at the different temperature. Likewise, if we had the temperature and pressure at two different points, we can calculate the vapor pressure of that substance. Now, when you're doing these types of problems, 90% of the time when you make a mistake, it's due to algebra. So one thing you have to remember is that delta H of vaporization is in kilojoules. R is in joules. So before you begin, I would recommend converting delta H into joules, so that way the joules cancel. So again, if you were just to plot vapor pressure versus temperature, you would have a non-linear plot. So there's not much we can do as far as linear regression for a non-linear plot. But if we were to take the ln of P and plot it against 1 over T, where T is in Kelvin, you see that we get a linear relationship. So then from the slope, which is this number, we can determine the delta H of vaporization. And just to make a note, delta H of vaporization is always a positive value. It is never going to be negative. So what that means is that when you go from a liquid to a gas, you release heat, which is incorrect. When you go from a liquid to a gas, you always absorb heat. So the equation is just negative delta H divided by R. Okay. So I'm going to go over one example with you to show you how we can calculate the vapor pressure at a different temperature given the vapor pressure at a temperature with the delta H of vaporization. And so since it gives us the temperature and vapor pressure, and the delta H of our substance, and we're asked to determine the vapor pressure at a new temperature. So again, one thing to notice is that the first set of vapor pressure and temperature, we're at 34.1 degrees Celsius, and it has a vapor pressure of 40.1 torr. We want to know what's the vapor pressure at 85 degrees Celsius. So notice here that we've increased the temperature. So our final vapor pressure should be greater than 40.1, because as you increase temperature, you're going to increase vapor pressure. So when we get our final answer, if it's not greater than 40.1, that's a serious mistake. It should be greater because, again, we increased temperature. So we're going to be using that 2-point form of the Clausius-Clapeyron equation. So our P1 is 40.1 torr, T1 34.5, and this is degrees Celsius, but we'll need to convert it to Kelvin. And by you add 273.15, you get Kelvin. So we get 307.65 Kelvin. Yes, I meant 34.1. So we get 307.25 Kelvin. Now T1 is 34, that's degrees Celsius, equals 307.25 Kelvin. I don't have the degree sign, so I use degrees Celsius equals Kelvin. So T1 is in Kelvin, and then P2 is what we're looking for, and T2 is 85 degrees C. That's just a unit degree C, and if we convert that to Kelvin, .358.15. So now we have the temperatures in Kelvin. We have our delta H of vaporization. We can set up the Clausius-Clapeyron equation. So ln of P2 divided by P1. Yeah. So R is 8.314 joule per mole Kelvin. Back to this, ln of P2, we don't know, divided by P1, which is 40.1, equals, now it's the negative of the delta H, so negative 40. So converted to joules, so negative 40,700 joules divided by R. So again, I went ahead and converted it to joules, delta H, because again, R is in joules, times 1 over T2 minus 1 over T1. You need to make sure you convert to Kelvin, because again, it's 1 over the temperature. It's not a change. It's 1 over the temperature of 1 minus 1 over the temperature of 2. It's a difference here, and you got to have units cancel. So make sure you convert to Kelvin, because that's what's required. Now, if we start solving this, we get ln of P2 divided by 40.1. And here I'm going to do it in steps. So we're going to take six times negative 4.626 e to the negative 4. So I just simplified the two expressions on the right side, and now I'm going to combine them. And notice that the two negatives cancel, which is what we want. And we get 2.2646. So now we get to this point. So you need to convert to either the delta H to joules or the R to kilojoules. And it's easier to convert kilojoules to joules. You get a larger number, less room, less likely to have error with larger number division than if you do smaller number division. If you wanted to keep kilojoules, then you just convert to R from joules to kilojoules. So now we take now we have ln of P2 divided by 40.1 equals 2.2646. We need to get rid of the ln, so we're going to raise each side to the power of e, and this is the small e, the exponential, not the capital E on your calculator. So we raise that side to the e, we raise this side to the e, the ln and the e cancel out, and we get P2 divided by 40.1 equals, again, if you want to find the e function as second ln on most calculators, is called the anti-ln. And you get 9.627, take 3. Now to find P2, we multiply both sides by 40.1. And we get 386 torque. So our answer is greater than 40.1, so at least we're on the right direction. So what I did is I took, to get the 9.6273, I did second ln on my calculator. I typed in 2.2646, and that gives me what the exponential of 2.2646 is. And then I multiply that 9.6273 by 40.1 to get 386 of torque. Double check. Yep. So that's how we would use the Clausius-Clapeyron equation. Oh, 314, sorry, that's a typo. Yeah, if it's 314, you get the 4,895. So now looking at the second example, here we want to calculate the delta H of a liquid that has a vapor pressure of 621 torr at 85.2 degrees Celsius and a boiling point of 95.6 at 1 atmosphere. So again, what we're looking for in this case is delta H. And as I said earlier, your delta H of vaporization is always going to be positive. So if you go through this exercise and you see a delta H of vaporization that is negative, you need to double check your work. So again, since we have a pressure and temperature and another pressure and temperature, we're going to be using the 2-point form of the Clausius-Clapeyron equation. And so again, P1 is 621 torr. P2 is 85 degrees Celsius, which we convert to Kelvin, or 85.2 degrees Celsius. And we're going to convert that to Kelvin by adding 273.15. We get 358. Okay. Now for P2, notice here that it's in atmospheres, so you have to convert either torr to atmospheres or atmospheres to torr. I recommend converting atmospheres to torr because torr is a larger number, less room for rounding error. So 1 atmosphere, as you should remember from Gym Chem 1, is 760 torr. And this should be, excuse me, that should be T1. Now for T2, we have 95.6 degrees Celsius. This equals 368.75 Kelvin. So now we're ready to set up our 2-point form of the Clausius-Clapeyron equation. So it would be ln of P2 760 divided by P1 621. Then we're going to have 1 over T2 minus 1 over T1. So again, we're getting the 1 over T2 minus 1 over T1. Now we're going to work some of this stuff out, simplify. By that part. We get an extremely small number. One, two, three, four, five. Negative 6. Let me double check my work. Oh. So now we're going to move this negative 7.8703 times 10 to the negative 5th to the other side by dividing both sides by this number. So when we do that, we get negative 2566.48. And that equals negative delta H divided by R. Now R is a constant. Remember, R is joule per mole Kelvin, 8.314 joules per mole Kelvin. So now we're going to multiply both sides by R. And notice here that the negative sign here and the negative sign here cancel out because two negatives cancel each other out. So now we have 2566.48. So again, I replaced R with its number 8.314, and now we get delta H. With 21,337.7. And this is in joules, but delta H is generally given in kilojoules, so this would be 21.34 kilojoules. So notice here again that delta H is positive, and that's what it should be. If it was negative, I would go back and double check your work.